This week we'll discuss data normalization and how it relates to the design process. So why do we normalize? Well, as we've seen in the past, ER modeling is one step in the design process. Normalization usually follows that step, sort of a secondary step in order to make sure that we can minimize or eliminate any redundancy problems which may crop up. If we have any such problems, we attempt to restructure tables to minimize that redundancy. Formally, we talk about functional dependencies. Functional dependencies are facts within entities or tables which can lead to redundancy. Our goal of this process is to prevent anomalies that happen when we insert, update, or delete data. These anomalies are unintended side effects from redundancy. However, sometimes it is a good idea to perform denormalization. In other words, to leave something unnormalized or to undo any normalization that was done previously based on the needs of the database. Normalization is update biased and is really not a concern for databases without updates. Often these are called data warehouses. And in fact, denormalization may improve performance, but depending on the cost, it may not be worthwhile or it may be worthwhile. Excessive redundancy can lead to other problems which may overturn any benefits in performance. So what are these modification anomalies? As I mentioned, they're unexpected side effects, but here's the three in particular we're concerned about. An insertion anomaly occurs when extra data beyond the desired data must be added. In other words, if we add a row of data to a database, we may need to add a second or a third or a fourth row just to make the data fit. An update anomaly occurs when it is necessary to change multiple rows to modify a single fact. To give you an example, Penn State maintains information about you, such as your name, your date of birth, and your student ID. An update anomaly would occur if, for example, you changed your student ID. If they needed to update more than one record to make that change happen, that would be an update anomaly. A deletion anomaly occurs when we need to delete a row. By deleting that row, if it inadvertently causes other data to be deleted, we have a deletion anomaly. Now, all of these anomalies are ultimately caused by excessive redundancy, and what we strive for in database design is the idea of one fact in one place, because redundancy leads to inconsistency. Inconsistency means that we have redundant data which becomes out of sync, which is really an undesirable property because data is just so important to any organization. And ultimately, redundancy and its side effects are a result of poor design. So we spend time up front to try and minimize and or eliminate redundancy and, by extension, inconsistency. Here's an example of a table which is poorly designed. This is a shipment table tying together three things: information about suppliers, information about parts, and information about shipments. In other words, what suppliers supply which parts. This is kind of a classic example that we often see in relational database literature. But the idea here is that we have a table, one table, which is very poorly designed. What we're going to talk about as we go through this process is how we can make this table more appropriately designed. Before we do that, let's talk a little bit about what are functional dependencies. And again, this is a concept you will have seen earlier in the semester in your reading, but let's formally define it now. Functional dependencies are a way of saying that the values contained in one or more non-key fields depend on, or conversely, are determined by, the values in one or more other non-key fields. This is a fancy way of saying that everything in a table should be a fact about the key, the whole key, and nothing but the key. Now, normally when we say key, we're talking about the primary key. Functional dependencies represent integrity constraints for a table, defining business rules. We strive to have this idea of one fact in one place, and an extension of that is we strive to have all the information about one thing contained within one table, at least as much as possible. So what does the formal definition look like? Well, functional dependencies, and in truth, the relational model, is mathematically based. So let's take a look at that formal definition. If we were to formally define this idea of functional dependence, we could say, let R be a table or a relation, and let X and Y be arbitrary subsets of the set of attributes of R. We can say that Y is functionally dependent on X, using this symbology with the arrow, if and only if, in every possible legal value of R, each X value has associated with it precisely one Y value. Whenever two records agree on their X value, they agree on their Y value. The left-hand side of the dependency is called the determinant. The right-hand side is called the dependent. Now this is a fancy way of saying that everything in the table should be a fact about the key, the whole key, and nothing but the key. If we have a well-designed table, everything on the right-hand side, the dependents, should be all of the non-key fields. The only thing that should be on the left-hand side, the determinant, should be the primary key, whether that's a single attribute or whether it's a composite primary key. With normalization, we're concerned about normal forms. A table is said to be in a particular normal form if it follows a set of conditions. For us, we're mainly concerned with normal forms 1 through 3, although there are more, such as normal forms 4 and 5 and Boyce-Codd normal form. They tend to be higher level forms. Normal forms 1 through 3 are the ones we're normally concerned about at the design level. After that, we often get into situations where normalization causes a decrease in performance that is often considered unacceptable. So here's what they are. A table is in first normal form if every cell has only one value. We get this by default in most, if not all, database management systems today. So we normally don't have to worry about that. What we have to worry about more is second normal form. This occurs when we have a composite primary key. A table violates second normal form, or 2NF, when a non-key attribute is functionally dependent upon a subset of the primary key. Formally written, violations of second normal form are when a part of a key determines a non-key. Now, the idea here is that, again, not everything in the table is a fact about the whole key. This is a problem often when you have information about two separate things stored in a single table. Now, when it comes to third normal form, a table violates third normal form, or 3NF, when a non-key attribute is functionally dependent upon another non-key attribute. A violation occurs when a non-key determines a non-key. This is often a problem as well, not necessarily just for things that have a composite key, but for tables which have a single primary key. So let's take a look here at what the normalization process involves. Really, when we talk about the normalization process, we're looking to see if we have any redundancy issues. We take a poorly designed table and we split it up in the hopes of reducing or eliminating that redundancy. By splitting up the table using projection, we're placing a badly designed table into a set of tables which meet the conditions for a more desirable normal form. This process is completely reversible and is intended to be information preserving. We don't want to lose any information, we just want to shuffle it around. Our goal is to create independent, non-loss projections, meaning we don't lose any data, and we can bring it back to the original using the join operator. So our decomposition operator is project. So when we talk about splitting tables and normalization, we're talking about projection. Our recomposition operator, if we want to bring everything back to the way it was, is join. So let's circle back to that shipment table idea. If we look at this table, it has a lot of information. Suppose we have a composite primary key for this table. S underscore meaning supplier number, and P underscore meaning part number. So what normal forms are violated, and how do we fix it? Well, let's take a moment to talk about what's in this table. Going from left to right, the first four fields, S underscore, S name, status, and city, are facts about the supplier. The next five fields, part number or P underscore, P name, color, weight, and P city, are facts about the part. P city indicates the city in which the part is manufactured. The last column, QTY, is a fact about the relationship between suppliers and parts. In other words, a given supplier supplies a given part, in a particular quantity, or QTY. Obviously, we have a lot of things stored within one table. This is a poorly designed table. So let's break it down a little bit. The shipment table violates second normal form because there are fields in this table representing facts about only part of the key, not the whole key. In other words, S name, status, and S city are facts about the supplier. Remember that supplier number, or S underscore, is part of the composite primary key. P name, color, weight, and P city are facts about the part. Remember that part number, or P underscore, is part of the composite primary key. So there we have a situation where we have a number of fields which are facts about only part of the whole key. So we have a problem, and this problem violates second normal form. So we say that this table is not in second normal form, or equivalently we can say this table violates second normal form. If we write this situation as functional dependencies in a more formal way, we can see those here with the last two bullet points. This is how we write in functional dependency notation the situation that we've encountered. The items on the left are the determinants. The items on the right are the dependents. Ideally, if we have a well-designed table, on the left you should have the entire primary key. We don't. For each of these functional dependencies, we only have part of the primary key as the determinant. That's a clue that this violates second normal form and that we've got to fix something. Luckily, these functional dependencies can help guide us as to how we fix it. So we can use these functional dependencies as our guide to creating two new tables. Each functional dependency translates into one table. Now, ultimately, these two tables are projections from the original table shipment. We can create a part table and a supplier table. For the part table, we use the functional dependency where P underscores the determinant, and that becomes the primary key of the new part table. The other fields within that table become the dependents, or are derived from the dependents. The supplier table, we have as its primary key the determinant from our functional dependency, supplier number, or S underscore, and the other fields are derived from the dependents, S name, status, and S city. Each of these tables, again, is a projection from the original shipment table. The design we just created, however, is not information preserving. The parts table and the supplier table were created from the functional dependencies that we encountered, and they represent projections from the original shipment table. However, if that's all we have, information is lost. We would lose one field from the original table, QTY, or quantity, and we would also lose the information about the shipment relationship, what suppliers supply which parts. Therefore, we need a third table, representing an associative entity, or what the book calls an intersection table, allowing us to maintain the information about the relationship. The table you see here on the right is called shipment. It maintains the information about which suppliers supply which parts in what quantity. The primary key is composite, being the composite of the supplier number and the part number. Both of these fields would also be foreign keys back to their respective tables. One last thing before we end our presentation. Something that's talked about in Chapter 4 and in Chapter 5 is the idea of a supertype and subtype. In this situation, it's not always about removing redundancy. The design is usually about trying to shuffle the information so that we minimize the number of fields which may be blank. In this particular example taken from the textbook, we have a student entity, or equivalently a student table, which has two subtypes, undergraduate and graduate, which, while they share a primary key, also have different attributes. Like undergraduate has high school GPA, whereas graduate student has undergraduate GPA, as well as score on GMATs. Now the idea here is that we represent this type of relationship using the symbology you see here, but also more than that, when we convert this to a table relationship, for undergraduate and graduate, they would be separate tables, and their primary key, student ID, would be a foreign key back to the supertype table, which in this case is called student. So while information about one student may be stored in 2 tables, or even 3, it's important to recognize why we restructure the tables this way. Take a moment to examine this little diagram and consider the possibilities as to why we break this down. If you think about a student, that student may be an undergraduate and may never be a graduate student, but often a student who's an undergraduate eventually becomes a graduate student. So we're going to have necessarily some redundancy here, in the sense that student ID is duplicated multiple times. However, with this design, we have minimized the amount of redundancy, and more importantly, we've minimized the amount of holes or blank cells we may have if we only had one table.